If instead of point charges we have a uniform field, like between two plates that are charged in a parallel plate capacitor, we end up with the simple situation we had with gravity in early physics 1. Here our field was G, and that was constant, and the potential difference between 2 points, not potential energy, but just potential difference, would have been G times H. Here, the uniform field is E, so the potential difference between the 2 points some distance d apart is E times d. Now, just as in the gravitational case, really the only distance that matters is the distance along the field. The length of this yellow arrow between A and B is not important. The only thing that matters is this purple arrow D, which is their distance along the direction of the field. The reason this is the only thing that's important is that the electrostatic field is conservative. That's why we have a potential energy associated with it. Now, where could we use voltage and have it be more useful than field in solving problems? What if we're in this uniform field, say we're between the plates of a parallel plate capacitor? We could find the speed of a charge after we let it go, after it moves a distance d, just by using A as QE over m, where Q is the charge's charge and m is its mass. The field inside the capacitor is constant, so the acceleration is also constant. Once we know A, we can just use the kinematic equations to get the velocity after some particular distance. What if the field isn't constant, though? Let's say we have a large charge plus Q glued down to one point in space and a free charge plus little q nearby at a distance r1. How fast is little q moving when it's reached a distance r2 from q? If we wanted to solve this problem with the electric field, it would require calculus because the acceleration is changing all along the path. Instead, we can use the fact that the voltage near Q1, for example at point R1, is kq over R1. We move from R1 to R2, which is going to be larger since these positive charges are going to move away from each other. Our potential energy will drop. We'll go from kq over R1 to kqq over R1 to kqq over R2. So our delta PE will be negative. That decrease in potential energy is balanced by an increase in kinetic energy. So if Q started with no velocity, it would end up at R2 with the speed given by this. Notice we've swapped the order of these two to take care of that negative. Now, that's a much easier solution than having to integrate the electric field. While we're talking about energy, though, there's a useful measure of it besides the joule, and it's called the electron volt, or EV. It's the energy we would get with moving a single electron across a potential difference of 1 volt. This is not a good unit for macroscopic objects since 1 joule is about 6 billion electron volts. We can now go back to the idea that the electric field in a conductor is zero in electrostatics, which is the first part of our course. This means no batteries or generators or changing magnetic fields, any of that stuff that we'll see later. So basically charges don't move except for the tiny fraction of a second it takes to adjust to things like a dumping of charge on some conductor. The reasoning is pretty simple. The main thing that makes a conductor, as far as we're concerned, is that there are free charges that are able to move wherever through that conductor. If we suddenly drop a charge inside a conductor, we're going to make an electric field. The free charges will respond to that electric field by moving until it's canceled. Again, you can think of this as being what would happen if you had an aquarium full of water and you scooped a cup of water out. Very quickly, the water level goes back to flat, what it was before. For the water, the time scale for that might be milliseconds, but for the conductor, it's more like billionths of a second or nanoseconds. Now, if the electric field is zero, like we're saying it is inside a conductor, does that tell us anything about the voltage? It doesn't tell us that the voltage is zero, and that's because E is a slope. So if it's zero, all we know is voltage is constant. It's the same everywhere. So in gravitational terms, just because the ground is flat doesn't mean we know anything about its height. There are going to be flat spots in Denver and in Death Valley. So the conductor is something that has the same potential everywhere, so we could call it an equipotential volume rather than surface. So all parts have the same potential. It may be zero, but it doesn't have to be. Now, we can make up and solve problems however we want. We can say we have a 6 coulomb charge sitting here in a spot the size of an atom. Are there complications if we do this in the real world? Yes. If we put too much charge in one place, we eventually make an electric field so strong that we break the air around it. Air has what's called a dielectric breakdown strength, and so does all other matter. This is the point beyond which an insulator becomes a conductor. So if you scuff your feet along the ground in the winter and touch a doorknob and see a little spark, that means the electric field produced there exceeded that breakdown strength. For air, it's about 3 million volts per meter. We can use this to make a guess at the voltage difference between 2 points when we see a spark jump between them. So let's say the spark from your finger to the doorknob is 1 centimeter long. If that's the case, if this is our breakdown field times that distance, we get 30,000 volts. Now, the electrodes in the spark plugs in your car, the gap between them is usually somewhere around a millimeter. That means the car has to be supplying a potential difference of 3,000 volts to keep that spark plug sparking. If you've ever been hit by a spark plug wire, you know that the voltage is incredibly high compared to what you might be expecting. It's certainly not the 12 volts of the car battery.